All right, so we're gonna talk about buffers today. All right, so a buffer is a solution that contains a weak acid and some of its conjugate base, all right, or a weak base and its conjugate acid. And the whole point of a buffer is to make a solution that is able to resist additional H plus or OH minus ions. Its goal is to try to keep the pH relatively constant. All right, so compared to a solution that's not buffered, all right, a buffer solution will have a more constant pH when acid or base is added. So, and the whole reason they can do this is because it has both a weak acid present and a conjugate base present, right? Or obviously vice versa, a base present and its conjugate acid. So if you have an acid present, you can react with hydroxide ions and neutralize them away, right? If you have a weak base, if you have a conjugate base present, it can react with H plus ions, and therefore it can also resist the change of pH. Right. So when you make a buffer, you have the concentration of your conjugate acid and base pair is really high. And because of this, it's able to resist pH changes. And it's able to resist this because the acid or the base is able to react completely with any extra H plus or OH minus ions. And when it reacts with them, even though some of the acid would be neutralized by the addition of hydroxide ions, or some of the base could be neutralized by the addition of H plus ions. The ratio of your acid conjugate base, base conjugate acid issue, or the ratio of those two substances, excuse me, stays basically the same. Our pH doesn't change by much. I think if you look at it like a chart, maybe it makes a little more sense. Maybe we'll draw this out. Let's draw it in. So in this container, we've got some HX. We'll give us let's give us 5HXs. So that's our weak acid. All right, and then let's put in blue our conjugate base. All right, and notice right now, right, we have 5 of each. So, the ratio HX over X minus equals 1. All right, that's like the ideal buffer. All right, we equal 1. All right, so along comes an H plus ion. All right, so here I'm adding something acidic. Now let's just think normally, right? If I have a beaker and my beaker just has water in it, right? Right. And let's say I add, just for argument's sake, 2 H plus ions. Well, when I add these 2 ions to water, there's nothing to react with the H plus ion. So my new solution is going to be H2O and 2 H pluses. And because there's nothing to neutralize this, right, this new solution is going to become it's going to become acidic. H plus greater than OH minus, all right, pH drops. That's all for that one up there, all right? Now, let's take a look at it, all right, in a different light. So let me do this. It's not as easy as the thing in the room, that's for sure. All right, so now I'm going to add these H pluses. Now I'm going to add them down here. Well, these H pluses, they're not going to react with the HX, right? They're not going to react with HS. But they will react with X minus. Well, guess what? If I add 2 H pluses, these guys go away, and these guys go away, and they they neutralize each other. All right. And now, if I were to do a ratio, let's do a new ratio in like purple over here. HX is greater than X minus, all right? And because we have more HX than X minus, all right, our pH is going to go down, but not as much because we, 8 neutralized the H pluses. So the pH still becomes more acidic because we made technically more of this weak acid. We made more HX ions, which are going to dissociate more and produce more H pluses later on down the road. But it's not as brutal as like the frontal attack of H pluses. Right? The exact same thing is true if we were to add hydroxides, but the OH minuses would attack or would be neutralized by the HXs. And instead of the scenario that's kind of depicted over here, we would get this scenario over here that I'll look at in yellow. That's if we added more bases. Right. All right. So which would produce a good buffer here? So let's first off think about this. We need a weak acid and its conjugate base, or we need a weak base and its conjugate acid. So first off, they have to be a pair, and they can't be strong acids or weak acid, or sorry, strong acids or strong bases. So A is no good because not a pair and both strong. So that doesn't work. B doesn't work because although HCl and Cl minus are pairs, all right, HCl is a strong acid. Okay. HF and H3, they work because they're weak acids and bases, but not pairs. They're not conjugates. So no, right? D works because we have the OCl minus ion and we have HOCl. That is a base and it's conjugate acid. Or you could write, conjugate base and acid. So there you go. So D, that would be a buffer. That's the only one that could be a buffer because this can react with H plus and this can react with OH minus, right? Let's go real quick. I want to look at why we couldn't use like letter B. So if we had a buffer made of B, we have, excuse me, H plus from the strong acid, right? And we would have Cl minus as our conjugate base, okay? If I add hydroxide ions, right, the hydroxide will be eaten up by the H plus and pH really won't change so much. So this can easily withstand the addition of hydroxide ions. That's no big deal. However, if I add H plus ions, this will not form. And it doesn't form because Cl minus is a weaker than water base. So if you add H plus, who else is sitting in this solution? H2O. Well, it's just going to react with the H2O, and it's going to go from H2O to H3O plus, and there is nothing to stop this from doing its thing. And if you add something acidic to this, the pH is just going to keep plummeting. There's nothing to stop it from dropping. So that's why it's not a buffer. Strong acids and bases can't be buffers because their conjugates can't react with the opposite. If you had a buffer made out of a strong acid and its conjugate base, because its conjugate base is weaker than water, that buffer cannot do anything to the addition of an acid. It'll just become more acidic. It can't neutralize an additional acid. Same thing if you had a strong base as a buffer, okay? And if you added something basic to it, a strong buffer's conjugate acid is so weak that if you add that base to it, that acid cannot do a thing to it. It's just going to react with water and it's just going to become more basic. So again, so idea that strong acids and weak or strong acids and strong bases, it's all about their conjugates not being able to do anything. Because they can't do anything, they can't be a buffer. All right. So this is another question. It's all about buffers again. So we got two solutions. All right. If we look, their volume and molarities are the same. The big difference is their Kas. We can make some quick assumptions real quick, or not assumptions. We can make some quick statements. All right. This Ka is less than 1. This is a weak acid. This Ka is greater than 1. This is a strong acid. Okay. So it wants to know what would happen if we added something basic to it. So look, if we're adding a base to this, okay, so it wants to know what's going to happen to the pH. All right. The pH of HA would be higher because NOH is a strong base. Well, this is true, but it's a strong base for everybody. So that doesn't really make any sense. So no. The pH of HA would be higher than HX because it forms a weak conjugate base. So HA, all right, is a weak acid. Therefore, it does form a conjugate base that raises pH. So B looks promising. C, the pH of HA would be lower than HX because it's a weak acid. So again, HA is a weak acid, but because HX is a strong acid, all right, its conjugate base does nothing, all right? And this conjugate also does nothing. So when you add equal amounts, molarity and volume, we are at equivalence point, right? Moles equal moles. So if it's a strong acid and strong base, at equivalence point, there's only water left over. Only water affects the pH. pH is 7, so C is no good. And then D, the pH of HA would be lower than HX because it forms water as a product. That's just a nonsense statement, so the answer is B. They both form water. All right, we got 4 acids. It says they're in no order: chlorous, hydrochloric, lactic, and proponic. Propanoic. A solution of acid 1 is mixed with a solution of sodium hydroxide. Which of the following best explains what happens to the pH of the mixture when a few drops of 1 molar nitric acid are added? So let's think this through. Forget about the question itself. Let's just think about this last part. All right. When HNO3 is added, all right, the pH should drop because the amount of H plus is increasing. All right. Now, if it's a buffer, right? If buffer, some of the H plus is neutralized and the pH goes down, but not as much. But this is only true if we're a buffer. Okay. Now remember that buffer needs to be a weak acid. Right? We need a weak acid. One of these acids, hydrochloric, is a strong acid. So as long as acid 1, right, we need acid 1, we got to figure out what it is. Is it a weak acid or is it a strong acid? We got to figure it out. Well, if it's a strong acid, right, strong acid fully dissociates. So if the concentration of the acid is 1, oh, I'm sorry, not 1. If the concentration of our acid, let's just take a look right here. Oh, yeah. We'll do this one right here. Easy one. The concentration of our acid is 1.0, then the concentration of H plus is also 1.0. All right. And then if we take the negative log of 1.0, we get 0. All right. So if we look, acid 1 at this part, its pH is not 0. So acid 1, not a weak, or sorry, it's not strong. So it must be a weak acid. That makes it a buffer. We've made a buffer. And because we have a buffered solution, all right, we get this down here. All right. The pH will decrease, but some of the H plus will neutralize by the X or A minus, whatever you want to call it, the conjugate base. Okay, so since we're based off of a buffer, buffering capacity is just how long we can basically absorb H or OH minus ions before we have significant pH change. Buffering capacity just in general, all right, is pH plus or minus 1 point. So if you have a pH of 4 as a buffer, all right, it can buffer up to a pH of 5 and down to 3. That's like the effective range. Once you get outside of, above 5 or below 3, if your buffer was at a 4, your buffer has broken. The buffer is no good anymore. The buffer died, basically. When you pick a buffer, you want to choose a weak acid that has a pK close to its desired pH, right? So if you want to have a buffer at 3.7 pH, then you want to pick an acid who has a pKa as close to 3.7 as possible. That's going to be your best buffer, right? If you pick a buffer that's really far away from that, then you've already broken your capacity. It's not going to. All right. And then to make any buffer, right now, this seems like I'm talking now totally backwards and I'm not making sense, but hear me out. To make the buffer, you take a weak acid and you add some strong base to it. The whole purpose is to do this. I have my weak acid. I add a strong base, OH minus. Remember, this is neutralization, so it goes to completion. Your products are H2O, okay, and X minus, okay? The goal, all right, is you start with, let's just say, 100 of this, okay? If I add 50 of the base, remember, these don't start as anything. Well, when this reaction goes to completion, all of this is gone. This drops to 50, and this goes up to, in this case, 50. Notice now, X minus and HX are the same. That's the best way to do a buffer, because now you have the maximum capacity to buffer, and your ratio of HX and X minus are the same. The buffer, back real quick, the buffer is still made of a weak acid and its conjugate base. Remember, all the strong base was destroyed. It was neutralized. We use the strong base to make the buffer, but it's not actually in the buffer, right? Its job was just to get the buffer going. The buffer contains no more strong base. All right, we will look at this equation more often. It's called the Henderson-Hasselbalch equation. It is provided for you, right? And then we talked about, want that ratio to be the same. Well, this is why. When this is true, okay, the log of 1 is 0, which means pH equals pKa. So if you wanted a pH of 5 and then you chose a pKa that was also 5, then you're good to go. When we look at titration graphs, we're going to get more into this, but just as a quick heads up, all right, this is just some basic stuff with logs. All right, the log of any number that is less than 1 is negative, the log of 1 is 0, and the log of any number that is larger than 1 is positive. So why does that matter? Just look at the ratio, all right? Our ratio for this equation is our base over our acid, okay? So if the base over the acid is greater than 1, then this back term goes up and the pH is greater than the pKa. Okay. If this is less than 1, meaning there's more acid than base, okay, the log of any number less than 1 is negative. That means this back term is negative. Now we're going to subtract. The pH is less than the pKa. Okay, this is technically before half equivalence. When they are the same, this whole back thing disappears and you're left with just that. Okay. So let's look at this. We have some acid. The pKa is 5.74. Explain how the pH solution containing HA and its conjugate base A minus would compare to the pKa. So we're not going to do any math here. We know, so write the equation out. pH equals pKa plus the log of A minus over HA. That's the equation, right? There's the equation. All right, well, let's just take a look real quick, all right? We have 1, 2, 3 HAs. We have 1, 2, 3, 4 A minuses, all right? So we have more base than our acid. Our log, all right, is going to be positive. Therefore, we're going to add something to our pKa. So it's going to be some number plus something, which means the pH has to be greater than the pKa, right? Because if this is 5.74, we're adding something to it. Even if we're adding the number 0.0001, we're still adding, which means pH is going to be bigger than that. This is really basic, just plug and chug. I don't really think you're ever gonna have to do one of these, but you would just plug it in. pH equals pKa, so that's the negative log of 1.8 times 10 to the negative fifth, all right, plus the log of HA over A minus, or sorry, A minus over HA. Well, A minus is that, all right, and that's the bottom. And then you would just type it in and solve. And I forgot my calculator at school, so I can't solve it for you. But I can tell you that here, because this ratio is positive, your pH will be above your pKa. All right, same thing here. All right, guys, any questions, please let me know. And again, write anything down that you didn't understand. All right, if you have to, watch it again. And then when I come back on Monday, we'll spend time going over all of this and the molecular structure stuff. So I can answer as many questions as you guys have. All right, have a good one.